Hello everyone, this is Team Benjamin and we are going to present geometric transformations. Part 1, Technical Details. First, let's define geometric transformations. The concept of operating of geometric transformations is an operation that is applied to the geometric description of an object to change its position, orientation, or size. Uses of geometric transformation, we can find uses for viewing routines that convert a world coordinate scene description to a display for an output device, or in computer aided design and computer animation. Also, we will find uses to describe how objects might move around in a scene during an animation sequence, or simply to view them from another angle. The first transformation we are going to explain is translations. We're going to start with 2D transformations and later another we're going to work with 3D transformations. A translation on a single coordinate point is performed by adding offsets to its coordinates. The translation distance pair tx dy is called a translation vector or shift vector. We can see this representation in the graph on the left side. P is the original point and P prime is the translated point. T in this case is representing the translation vector. The blue arrows are representing the components of this vector. The equation to generate a translated point is defined by x prime equals to original x plus the translation coordinate in x, and similarly y prime is going to be the original y plus the translation in the y-axis. In the case of a polygon, it is translated by adding a translation vector to the coordinate position of each vertex and then regenerating the polygon using the new set of vertex coordinates. We can observe this with the red arrows in the graph to the left. A translation is a rigid body transformation. This means that the object or polygon, the triangle in this case, is not deformed after the transformation or during the transformation. The matrix notation. It is possible to express the previous equation as a single matrix, but by using column vectors to represent coordinate positions and the translation vector. As we can observe here, if we define P, the original point, as a column vector xy, and P prime as a column vector x prime y prime, and the translation as tx ty, then we can rewrite the two-dimensional equation in the matrix form P prime equals P plus T. The following is the code of a function to perform the translation transformation in 2 dimensions. The function receives a set of vertex, a value for number of vertex, and the translation in x and the translation factor in y. The logic of this operation iterates over each vertex and generates a new vertex or a new set of vertex by adding the translation shift to each of their coordinates. After having the new set of coordinates, the polygon is regenerated. Rotation. To perform a rotation over an object, a rotation axis and a rotation angle must be defined. All the points of the object are then transformed to new positions by rotating the points through the specific angle about the rotation axis. In this case, the rotation axis is this dot, and the theta is going to be the angle to be rotated. this triangle is going to rotate each of its vertex. For example, this vertex is going to rotate a theta angle, this vertex is going to rotate a theta angle, and this vertex is going to rotate a theta angle. And then after those vertex are rotated, then the new triangle or the rotated triangle is going to be redrawn. In the case of a 2D rotation, the rotation axis is perpendicular to the xy plane. In this case, the parameters are theta, the rotation angle, and a rotation point instead of a rotation axis, represented by xr, yr. The rotation of a point when the pivot point is at the coordinate origin can be represented by the following variables. R is the distance of the point to the origin, the original point. Phi is the original angular position. We can see this here in the picture. This is the original P. This is the original, angular position of this point P. And theta is going to be the rotation angle, the desired rotation. If we perform this rotation, then we can observe that the new P or P prime coordinates are going to be defined by R, that's the distance to the origin, multiplied by the cosine of the sum of these two angles, phi and theta. We can observe that here. Similarly, we can apply for y using the sin function. And if we apply trigonometric identities, we can obtain this formula. We can observe that r cosine of theta, of phi, is equal to x. So we can replace x here, and we can replace in the similar way y in this portion of the equation. So we are going to end up with this set of equations that depends only on the original point coordinates and the desired angle. The matrix notation. If we have P defined as xy and P prime defined as x prime, y prime, and if we define the rotation matrix as we can show, we can see here in the slide, then we can rewrite the rotation equation in the form P prime equals R times P. If the 2D rotation is with respect to an arbitrary point, then it is possible to generalize the previous equation as we can see here. So in this case, x, that originally was this distance, now since this is not the origin, then we need to define which is this distance. This is x minus xr, that is the rotation point. Similarly, y, this will be the original y minus the rotation point in y. The rotations are rigid body transformations. Again, in this case, the polygon vertex, if we are going to rotate a polygon, every vertex is going to be rotated, and then the polygon is regenerated. Defining points of a curve, in the case of a curve, we're going to rotate the defining point and redraw the curve. And in the case of a circle, the center is moved through an arc, and then we are going to redraw the circle. Again, this is a function using OpenGL that rotate a polygon. We receive a set of vertex, a number of vertex, a pivot point, and a desired angle to be rotated. We go over each of the vertex and rotate them. And with a new set of vertex, we're going to regenerate the polygon. Transformation scaling. That's the third transformation in 2D. A simple 2D scaling transformation is performed by multiplying object's position xy by a scaling factor sx and xy. The function that describes this transformation is x prime equals the original x times fx, and y prime equals to the original y times sy. The 2D scaling transformation can be written in the matrix form x prime y prime equals to the matrix, the transformation matrix for scaling, times the column vector for P. So we will end up with P prime equals S times P. Any positive number can be assigned to scaling factors. When the scaling factors are equal, a uniform scaling is generated. When scaling factors are not equal, a differential scaling is produced. In some cases, some systems accept negative scaling factors, which this in turn will resize and reflect the object. The sample figure to the left will translate scale this figure A into this figure B. The scaling factors are x equals 2 and sy equals 1. These two in the scaling factor in x, we can see that the value for x is multiplied by 2, while the value for the y coordinates are kept the same because the scaling factor is 1. When objects transformed with the scaling matrix equation are both scaled and repositioned. Scaling factor with values less than 1 will move the object closer to the origin coordinate, and scaling factors with value greater than 1 will move the coordinate position farther from origin. In the example to the left, we can see that this line is transformed, is scaled by 0.5. This is a uniform transformation. So it will be closer to the x, will be reduced closer to the origin, and in y also will be close to the origin, this point. And at the same time, the line is scaled by a half. It is possible to control the location of a scaled object by choosing a position called the fixed point. So we are going to redefine the previous equations as x prime minus xf, that is the fixed point, equals to x minus xf times fx. Similarly for y prime minus yf will be equal to y minus yf, the fixed point, in y, times sy. This will be changed or reformulated, as we can see here, and we can notice that these adding factors to the right are going to be constant, because the xf and yf are constant values for all of the vertex, and 1 minus sx and 1 minus sy are also constant because x and sy are the scaling factors that are the same for all of the vertex. This is the scaling function for a polygon. We receive again a set of vertex, a number of vertex, a fixed point, a scaling factor in x, and a scaling factor in y. We're going to iterate over each vertex, and we are going to scale it by the factor and according to the fixed point. And with the new set of vertex, we're going to regenerate the polygon. Homogeneous coordinates. Sometimes, or most of the time, animations might require that an object to be translated and rotated at each increment of the motion. This can be represented as P prime, that's the new state of the object, will be M1, the matrix 1, times P, or P is the original point plus M2. M1 here is a 2 by 2 matrix for rotation and scaling. M2 is going to be a column vector for translation. Matrix representation can be reformulated so that transformation sequence can be processed efficiently. A more efficient approach is to combine transformation. We're going to talk about later about combined transformation. For now, let's focus on the representation. Homogeneous coordinate. Multiplicative and translational terms for a two-dimensional geometric transformation can be combined into a single matrix if we expand the representation to a 3 by 2 matrix. The third column can be used then for the translation terms. But we need to expand the matrix representation of a coordinate position xy to xh, yh, and h. This is called a homogeneous coordinate. In such case, x is going to be equals to xh divided by h, and y is going to be jh divided by h. Therefore, a 2D homogeneous coordinate could be written as h times x, h times y, and h. We define h times x is equal to xh, as we can see here. Normally, h is selected as a non-zero value and normally equal to 1 most of the time. The term homogeneous coordinate is used in mathematics to refer to the effect of this representation on Cartesian equations. When a Cartesian point xy is converted to a homogeneous representation, the equation containing x and y, such as fx equals 0, becomes homogeneous equations in the three parameters xh, yh, and h. Expressing positions in homogeneous coordinates allow us to represent all geometric transformation equations as matrix multiplication, which is the standard method used in graphic systems. So here are the translation matrix for using homogeneous coordinates. We can represent the equation for a two-dimensional translation for a coordinate position as we can see here. So basically, the third column will have the translation shift in x and in y. And in the bottom, we have an example for this. We suggest you to pause the video and pay attention to the multiplication of the numbers. In the case of a rotation matrix, the two-dimensional rotation transformation equation about the coordinate origin can be expressed in the matrix form. We can observe that these first two columns and first two rows correspond to the rotation matrix, the original rotation matrix. In this case, the values or the column for a shift or for a translation is equal to 0, except for the one in this column. Okay. Again, in the bottom part, we have an example that you can check for a small test, a simple test. The scaling matrix using homogeneous coordinate can be represented as follows. We're going to put the scaling factor for x in the first corner of the matrix. In the position 0, 0, in the position 1 and 1, we're going to use sy, the scaling factor for y, and then a 1 in the last corner of the matrix. Again, at the bottom, we have an example, so we can check on numbers. This inverse transformations. Inverse transformations are also called opposite transformations. An inverse geometric transformation performs the opposite operation performed by the original transformation. An inverse transformation is applied in a similar way as the original transformation. The multiplication of any 2D transformation matrix at its inverse will produce the identity matrix. How do we obtain the inverse transformation matrix? In the case of a translation, the inverse translation matrix is obtained by negating the translation distances. So for example, if this is the original transformation, the inverse transformation will be generated by minus tx minus ty in the place of tx and ty. For rotation, an inverse rotation is accomplished by replacing the rotation angle by its negative. So for example, if we have cosine of theta, we're going to replace it by cosine of minus theta, but it's the same. In the case of sin of minus sin of theta, we know that the sine of minus theta is going to be minus sine of theta. Then we obtain this new matrix as the rotation matrix for inverse transformation. And finally, the inverse transformation for scaling, we're going to generate this matrix by replacing the scaling parameters with their reciprocals. So we replace Sx by 1 over Sx and Sy by 1 over Sy. This is the inverse transformation for scaling. So this is all. Now my classmate, teammate Xiao Han is going to present the next part. Thank you.